Have you ever stared at the periodic table and felt like there was some kind of secret language hidden in those patterns?
Mm.
How elements, these basic building blocks of everything, are so diverse, yet they follow such clear, really fascinating rules. Well, get ready for a shortcut to truly understanding that hidden logic. Today, we're taking a deep dive into the periodic properties of the elements. We're not just like memorizing a chart. We're digging into the why behind how elements behave, how they interact, and how they literally shape our world.
It's absolutely true. At first glance, the chemical world can seem a bit chaotic, maybe. But the periodic table, well, it reveals this beautiful, almost predictive order. Our journey today will connect those fundamental concepts like atomic structure, which, we've touched on before, to the actual observable properties of elements.
Yeah.
You'll see how these connections reveal some surprising facts and how they translate into real-world things from the phone in your pocket to, well, the air you breathe.
Okay, so let's unpack this big story. How did we even start trying to categorize these building blocks? I mean, elements like gold, they've been known forever, right? Found just lying around.
And then their elemental form.
But then you have others, like technetium, which are unstable, only known because of modern tech. With so many elements hidden in compounds initially, what was the big challenge? Just keeping track? Or was it something deeper?
That's a great question. It was definitely more than just making a list. By the early 1800s, chemistry was getting much better at pulling elements out of compounds. So the number of known elements just exploded. Think about it, 31 in 1800 to 63 by 1865.
Wow, that's fast.
Yeah. So this flood of new information created this urgent need for organization for a system.
And that led to a really key moment in 1869. Two scientists, Dmitry Mendeleev in Russia and Lothar Meyer in Germany, they independently published remarkably similar ways to classify elements.
Independently. Yeah, and they both arranged elements by increasing atomic weight, and crucially, they both noticed that similar properties popped up again and again periodically.
Now, Mendeleev usually gets the lion's share of the credit here. What made his approach stand out so much, especially if Meyer was doing similar work? Was it just like better PR?
Not really PR, no. It was more about foresight and, honestly, boldness. While both use atomic weight, Mendeleev was just way more daring. He didn't just organize what was known, he predicted. He actually left blank spaces in his table.
Gaps.
Really? Yes. Because he believed undiscovered elements had to exist to fit the patterns. He even predicted their properties, like ecosilicon, which we now know is germanium, and his predictions astoundingly accurate. We're talking atomic weight predictions off by just tiny fractions, densities almost spot on. It was a massive triumph of scientific thinking.
Okay, but here's where it gets really interesting and kind of clears up some old puzzles. Mendeleev's table, brilliant as it was, still had a few weird spots based on atomic weight, right? Who finally sorted those out.
Right. That would be Henry Moseley, an English physicist in 1913. His contribution was absolutely crucial. He used X-ray frequencies. From these, he assigned a unique atomic number to each element, and he correctly figured out this number was the count of protons in the nucleus.
Ah, protons. So that's the fundamental ordering principle, not weight.
Exactly. This one insight was revolutionary. It completely fixed those inconsistencies where atomic weight order just didn't match chemical behavior. Think argon and potassium. Argon's heavier, but it's clearly a noble gas, unreactive. Potassium's lighter, but super reactive, like other alkali metals.
Right. Atomic weight puts them in the wrong spots chemically.
Precisely. Moseley's atomic number put argon, 18 protons, before potassium, 19 protons, perfectly aligning them with their chemical families. It solidified the modern periodic table we use today.
Okay, so to really get why elements behave the way they do, we need to look inside the atom. Let's talk effective nuclear charge, Zeph. How can we visualize that? It sounds a bit abstract.
It can be, yeah. Let's try an analogy. Imagine the nucleus is like a really bright light bulb. And the outer electron you care about, the valence electron, is someone looking at that bulb. Now, all the other electrons, especially the ones closer to the nucleus, the core electrons, they act like a frosted glass lampshade. They block some of the light.
Okay, like shielding.
Exactly, shielding or screening. So Zeph is the net positive charge, the amount of light or pull that the outer electron actually feels from the nucleus after you account for that shielding effect. It's always less than the total nuclear charge, but it's the effective pull that really dictates behavior.
And this Zeph, it shows clear trends on the table, doesn't it? Like moving left to right across a period, it generally goes up. Why is that?
Yeah, it increases across a period. It's because you're adding protons to the nucleus, making the light bulb brighter, but the number of core electrons doing the shielding stays the same. The lampshade isn't getting thicker.
So stronger pull on those outer electrons.
Exactly. It pulls those valence electrons in closer. This increasing Zeph is like the master key. It explains why elements shift from being metals wanting to lose electrons on the left to nonmetals wanting to gain electrons on the right. Going down a column, Zeph increases too, but only slightly. You're adding more core electrons, sure, but they're in shells further out, more diffuse. So they don't screen quite as effectively relative to the increased nuclear charge.
Okay, so if Zeph is pulling electrons closer across a period, what does that do to the actual size of the atom? Because atoms don't have sharp edges, right? How do we even measure them?
Good point. No hard boundaries. We usually talk about the bonding atomic radius. Basically, you take two atoms bonded together, measure the distance between their nuclei, and cut it in half. It gives us a practical way to think about how atoms fit together in molecules and compounds.
Right, so the trends. Down a group.
Down a group, atomic radius tends to increase. You're adding new electron shells, higher principal quantum numbers, so the outermost electrons are just physically further from the nucleus. Makes sense?
And across a period, left to right.
It generally decreases, and that comes straight back to Zeph. That increasing effective nuclear charge pulls the valence electron cloud in tighter, shrinking the atom.
Okay, what about ions? When atoms gain or lose electrons, how does their size change?
Right, ionic radii. Cations, positive ions formed by losing electrons, are always smaller than the original atom. They've lost that outer shell, and there's less electron repulsion pushing things apart.
Makes sense. And anions, negative ions.
Anions, formed by gaining electrons, are always larger than the parent atom. You've added more electrons, increased the repulsion between them, so the electron cloud puffs out.
And you mentioned something called an isoelectronic series.
Yeah. That's a set of ions, or maybe an atom and ions, that all have the same number of electrons, like O, AO, MRU, Aluro. They all have 10 electrons, same as neon. In a series like that, the size decreases as the nuclear charge, the number of protons goes up. More protons pulling on the same electron cloud means it gets pulled in tighter.
Wow, okay. These concepts, Zeph, atomic size, ionic size, they sound theoretical,
Yeah.
but they have huge real-world impacts, don't they? Like lithium-ion batteries.
Oh, absolutely. That's a perfect example. Lithium-ion batteries power almost everything now, right? Phones, laptops, EVs. The reason they work so well comes down to the lithium-ion layer. It's really small and only has a +1 charge.
And that matters because
Because it allows those ions to move really easily, really efficiently, back and forth between the battery's electrodes, the graphite anode, and the lithium cobalt oxide cathode. Usually when you charge and discharge it, they can slip in and out of the electrode materials.
oh,
If you try using larger ions, like sodium ions, no, which people are looking at because sodium is so much more abundant, well, it's much harder. Their larger size makes it difficult for them to move in and out of the electrode structures efficiently. It limits the battery's capacity and speed.
so the tiny size of lithium is key. That's fascinating. Okay, from size, let's shift to energy. Specifically, the energy needed to mess with electrons. Let's start with ionization energy. What is that exactly?
Right, ionization energy, or IE, it's the minimum energy you need to remove an electron from a gaseous atom or ion. We talk about the first ionization energy, I1, to remove the very first, outermost electron, then I2 for the second, I3 for the third, and so on.
Okay, and I assume it gets harder each time.
Always. Successive ionization energies always increase. Think about it. You're pulling a negative electron away from an increasingly positive ion. The attraction gets stronger, so it takes more energy. And there's a really dramatic jump in energy when you try to remove a core electron, one of those inner non-valence electrons.
Why such a big jump?
Because those core electrons are much closer to the nucleus and feel a much stronger effective nuclear charge. They're held incredibly tightly. That huge jump is basically proof that chemistry happens mostly with the outermost valence electrons. The core electrons just kind of watch.
Okay, so focusing on that first ionization energy, I1, what are the general trends on the periodic table?
Generally, I1 increases as you go from left to right across a period. Again, it connects back to Zeph and atomic size. Higher Zeph, smaller atom, means electrons are held more tightly, harder to remove.
So noble gases would have the highest I1 in their period.
Exactly. They really don't want to give up any electrons. Conversely, I1 generally decreases as you go down a column. The outermost electron is further from the nucleus. In a higher energy shell, feels less pull, so it's easier to remove.
But like always in chemistry, there are exceptions, little quirks in the trends.
Oh, definitely. And they tell us interesting things. For example, look at beryllium and boron. Boron is to the right, so you'd expect it to have a higher I1, but beryllium's is actually higher.
Why is that?
It's about electron configuration. Beryllium has a full 2s subshell. Boron adds 1 electron to the 2p subshell. That 2p electron is slightly higher in energy and a bit shielded by the 2s electrons, so it's actually a tiny bit easier to remove than one of beryllium's 2s electrons. Similarly, nitrogen has a higher I1 than oxygen next door. Nitrogen has a nice, stable, half-filled p subshell, 1 electron in each p orbital. Oxygen has 4 p electrons, meaning 1 p orbital has a pair. That repulsion between the paired electrons makes one of them slightly easier to remove.
Ah, so the little irregularities actually reinforce the models of electron configuration and stability. Okay, now let's flip the coin. Instead of removing electrons, what about gaining them? That brings us to electron affinity, EA.
Exactly. Electron affinity is the energy change that occurs when a gaseous atom gains an electron to form an anion, a negative ion. Now, the sign convention can be a little confusing. If energy is released when the electron is added, meaning the process is favorable and the anion is stable, the EA value is negative.
Okay, negative EA means it wants the electron, energetically speaking.
Pretty much, yeah. If energy has to be absorbed to force the electron onto the atom, the EA is positive, meaning the resulting anion is unstable.
So who has the most negative EAs? Who really wants electrons?
That would be the halogens, group 17, like fluorine, chlorine. They are just 1 electron away from having a stable noble gas configuration. Gaining that 1 electron is really favorable, so they release a lot of energy, very negative EAs.
And the opposite. Who doesn't want electrons?
Well, the noble gases, group 18, they already have a stable configuration, so adding another electron would mean putting it into a new, much higher energy shell. Very unfavorable, so positive EAs. Also, elements like beryllium and magnesium, group 2, have positive or near 0 EAs because the added electron would have to go into an empty, higher energy p subshell. And similar to the IE quirk, group 15 elements like nitrogen have less negative EAs than you might expect because adding an electron disrupts their stable, half-filled p subshell.
Okay, so we've got size, Zeph, ionization energy, electron affinity. These fundamental properties really define an element's chemical personality, don't they? This lets us group them broadly into metals, nonmetals, and metalloids.
Absolutely. Metals dominate the left side and center of the table. Think shiny luster, malleable, you can hammer them flat, ductile, you can draw them into wires, and they're great conductors of heat and electricity.
Right, typical metal properties.
Nonmetals are mostly in the upper right corner. They tend to lack luster, are often brittle if they're solid, and are poor conductors. They can be solids, liquids, or gases at room temp. And there's this idea of metallic character, which basically increases as you go down in group and decreases as you go left to right across a period. Low ionization energy is really the hallmark of a metal easily giving up electrons.
And how does this difference play out in their chemical reactions, especially with something common like oxygen?
Good question. Metals, because they lose electrons easily, low IE, form positive ions, excitations. Their oxides, when they react with oxygen, are typically basic. They react with water to form metal hydroxides or react with acids to form salts and water. Think rust, iron oxide, reacting slowly.
Okay, basic oxides from metals.
Nonmetals, on the other hand, tend to gain electrons, negative EA, or share them. They form negative ions, anions with metals, or molecular compounds with other nonmetals. Their oxides are typically acidic. Think carbon dioxide, TORO. It dissolves in water to form carbonic acid, that's the fizz in your soda, but also contributes to acid rain. Non-metal oxides react with bases.
And squeezed between them are the metalloids?
Yeah, the metalloids or semimetals along that sort of diagonal line. They have properties intermediate between metals and nonmetals. Silicon is the classic example. Looks kind of metallic, but it's brittle, not malleable. And crucially, it's a semiconductor. Its ability to conduct electricity is in between a conductor and an insulator, and we can control it. That property is the foundation of modern electronics, computer chips, everything.
Amazing how that intermediate property is so vital. Okay, let's quickly dive into a few specific groups to see these trends in action. Group 1, the alkali metals.
Ah, yes. Lithium, sodium, potassium, etc. These are soft, silvery metals, low density, low melting points. But the main thing, they are incredibly reactive.
Why so reactive?
It goes straight back to that very low first ionization energy. They have just one valence electron in that outer orbital, and they are extremely eager to lose it to form a stable +1 ion. This leads to really vigorous reactions, especially with water. Potassium, for instance, reacts so violently it ignites the hydrogen gas produced.
Wow.
And their reactions with oxygen are interesting too. Lithium forms a normal oxide, Li-oro. Sodium mostly forms a peroxide. And potassium, rubidium, cesium form superoxides like KO. Because they're so reactive, you have to store them under oil to keep them away from air and moisture.
And there's a surprising life connection here, right, with lithium.
Oh yeah, the chemistry and life bit. In the 1940s, it was discovered, somewhat accidentally, that lithium ions, usually given as lithium carbonate, have this remarkable stabilizing effect on people with bipolar disorder. It helps smooth out those extreme mood swings.
That's incredible. And you mentioned 7UP.
Believe it or not, yes. Early formulations of 7UP actually contained lithium citrate. It was marketed as a mood-lifting drink. Obviously, that changed significantly with modern understanding and regulations.
Wow, okay. Times have changed. Let's move next door to Group 2, the alkaline earth metals. How do they compare?
Okay, Group 2, beryllium, magnesium, calcium, and so on. Compared to Group 1, they're generally harder, denser, have higher melting points. Still very reactive, but definitely less violently so than the alkali metals. They tend to lose their 2 valence electrons to form 2+ ions.
And their reactivity with water?
It varies more down the group. Beryllium pretty much doesn't react. Magnesium reacts, but slowly, unless the water's boiling. But calcium, strontium, and barium react readily with cold water. And they have some nice visual applications. Strontium salts give you those brilliant reds and fireworks, and barium salts give you greens.
Cool. Now, let's talk about hydrogen. It sits over Group 1, but it's different, isn't it?
Oh, completely unique. It has that one-stay electron configuration like alkali metals, but that's where the similarity ends. Its ionization energy is actually really high, much closer to nonmetals like oxygen. So chemically, it behaves like a nonmetal. It shares electrons to form molecular compounds. Water, ammonia, NH, methane, CH are everywhere. But it can also gain an electron from very reactive metals to form the hydride ion, H none. So it's versatile.
And it has a bit of a dramatic history.
Yeah, the Hindenburg disaster is the famous tragic example of hydrogen's high flammability when mixed with oxygen. But today, that same reactivity is being harnessed potentially very positively in hydrogen fuel cells.
Right. Okay, jump across the table to Group 17, the halogens.
Fluorine, chlorine, bromine, iodine. Their chemistry is really dominated by those highly negative electron affinities we talked about. They desperately want to gain one electron to get that stable, noble gas configuration forming one halide ions.
And they're pretty reactive, too.
Extremely. Fluorine is the most reactive element known. It even reacts aggressively with water. Chlorine is also very reactive, a powerful oxidizing agent, which is why it's so useful as a disinfectant in water treatment and pools. Iodine is less reactive but essential for us biologically for thyroid function, hence iodized salt.
And finally, Group 18, the noble gases, helium, neon, argon, the unreactive bunch.
Traditionally called the inert gases. They're monatomic gases. They have completely filled outer S and P subshells. This makes for very high ionization energies and, yes, generally exceptional unreactivity.
Not completely unreactive.
Not completely. That inert label got seriously challenged back in 1962. Neil Bartlett, a chemist, managed to synthesize the first compound of a noble gas. He reacted xenon with a highly oxidizing fluorine compound. It proved that even these elements could be coaxed into forming chemical bonds under the right conditions. Xenon reacts directly with fluorine to make things like SF, Se, SeO. Krypton, being smaller with a higher IE, is less reactive. Only KrEFO is really known. And even argon, tiny argon, has been forced into making HRF, but only stable at super low temperatures.
So inert was more of a suggestion than a strict rule.
Kind of, yeah. It shows that chemical reactivity is a spectrum heavily influenced by those periodic properties like ionization energy.
So wrapping this up, we've really seen how the periodic table isn't just some static chart. It's this incredibly powerful predictive map. Understanding these trend size, Zeph, i.e. EA, unlocks the fundamental nature of the elements.
Absolutely. It explains their whole chemical personality from how easily they lose or gain electrons to the types of compounds they form.
And these core ideas, they explain so much around us. You know, how lithium batteries work, why hydrogen is both dangerous and a potential fuel source, the colors in fireworks, even the chemistry happening inside our own bodies.
It's all interconnected based on these fundamental atomic properties laid out so elegantly in the periodic table.
So the next time you glance at that table, maybe think about these underlying forces. What new questions pop into your head? What other hidden patterns are just waiting to be uncovered in the world around us, all thanks to the elements?
Thank you for joining us on this deep dive.